An introduction to forces and Newton's laws. So if you think back to middle school science and the general science course you took, you learn about Newton, how there's 3 laws and everything, but we're going to go into a lot more detail here than you ever have. So the first section is really an overview of the idea of forces and where they come from. So we're going to really discover how they affect motion, talk about 2 types of forces, and then talk about something called an FBD, or free body diagram. All right, those 3. So first, the force, or the definition of the word force, not the force like in Star Wars, but the definition of the word force, is something that causes an acceleration, okay, or a change in velocity. And if I think about it, if I take a simple eraser, and I'm going to use an example that's very easy because there's very little friction here. Even if I apply the tiniest force, it starts to move. The only way this can start to move is if its velocity went from 0 to something else. And whenever there's a change in velocity, there is acceleration. Hence the cause of acceleration. Now, obviously, if I were to do this to this table, it's not going to move, right? How come? It's heavy, sure, it's got a lot of inertia, a lot of mass. Why else? Not enough force for me to move it. What's repelling this motion?
Force is not strong.
What is? Friction, right? Friction is what keeps things from not moving when we push on them, really? Like granted, this wall, it's not friction, right? This wall is fixed, you would say. It's not a free body, it's fixed. So if I push on this wall, it pushes back. Equal and opposite, but I don't feel it pushing back, but I know it is. If you couldn't push back enough, my hand will go through the wall. That's what happens with like your calculator here. If your calculator weighed too much for the table wouldn't be able to push back enough, and the calculator would break through the table. That's not physically reasonable because we know the mass of the calculator, or its inertia, is very little, right? So, when we're looking here, when we think about this, even the smallest force on a free object will cause some motion. And think about an example. If you've seen the movie Gravity, or just think about space, anything you physically do will cause motion. So, if there was something in space floating by you very slowly, and you smacked it, it would go off with a certain velocity that way forever. Because there's no force that's going to slow it down. There might be the force of gravity pulling it into orbit around a planet eventually, or maybe around like a comet, but it's going to move freely because it's a free body. So when we discuss the idea of force and say it causes accelerations, we're assuming you're pushing a free body. Now, we'll see in this chapter what happens when there's opposing forces like friction. Okay, that obviously acceleration doesn't happen because you don't overcome that friction. You have to push enough to get past what we call static friction. So again, it's a cause of an acceleration. We generally describe a force as a push or a pull. Almost anything you do can be described that way, actually. As a push or a pull. Any physical motion. When I take a step, I'm pushing off the ground, actually. I'm literally pushing against the ground. I'm using friction to help me right now when I take a step. Let's see, if you were to lift something on like a conveyor, or you had like a pulley system, you need to lift a piano up to like a 3rd floor of a structure, you would have a pull, and you'd be pulling down, you'd be pulling up. And that pull would be the tension in the cord, really. That's what the force would be. So it's generally a push or a pull. Now, this is the weird part. So the unit of measurement for forces, we've heard of Newton before as Isaac Newton, but the unit here is going to be newtons. Just like a force can be measured in pounds. Like your weight. When you go to the doctor's office, they measure your weight, your height, all that stuff. They're measuring your pounds, really. They're not measuring the kilograms, which is your mass. They're measuring your weight, which is a force down, or the force of gravity. So in the SI unit, or the SI system of units, we use newtons instead of pounds. Okay? Instead of pounds. So Newton is a force. Now, it's made up of several things. And we're not going to get to this equation until next class, but I thought to show the units, it makes more sense. Okay, so what do you guys know of one of Newton's laws that's an equation? Does anybody remember what the only equation one says? Yeah, this is one from general science that you've learned. We're going to learn this in section 4.2. We'll go over where it comes from, everything. But just to demonstrate the units, it makes sense. So let me discuss. So the units over here for force we know are newtons, right? What are the units of mass? Think back. What's the units of mass? Grams. Now, that's the base unit. In physics, in the macro scale, we actually use kilograms as our base unit, which I haven't gone into yet. I'm going to talk about that tomorrow. So let's use kilograms, but gram is that base unit. Very good. Okay, so we usually talk about mass of objects in kilograms on a macro scale, meaning like real world. if you were looking on a micro scale, then you would use things smaller than grams. You'd use like atomic mass units, which you talked about in chemistry. So it depends on the scale you're looking at. For the sake of real world physics, it's kilograms. What's acceleration measured in? What's acceleration? What are the units of that? Come on, you guys, negative 9.81. Thank you. And so blank looks. You should know this by now for sure. If you just remember, acceleration of gravity is negative 9.81 meters per second squared. That's your acceleration units. So take a look. It's kilograms times meters over second squared. That's what that is really saying up top. I know there's a minus sign. It's actually on purpose. It's not a mistake. When you represent units mathematically, instead of writing kgm all over s squared, which would look kind of like this, if I wrote it in one line, it's a little bit confusing. I don't know why physicists haven't adopted just putting like a time symbol there instead, but with units they put a hyphen. It's not really a minus sign. It's a smaller one. Like if you were to write like x minus y versus something like this. It's supposed to be a hyphen. You ever look on the computer, if you like enter a hyphen, it could be short or it could be a longer hyphen. I know that's really weird, but that's how you can really distinguish. It's like a shorter hyphen. Okay, that's what that means up there, but just so you're used to it. This is the first unit you've seen this year that's comprised of other units. Right, so everything we've talked about so far has been like meters, seconds. Oh, actually we've done, sorry, I shouldn't say that. We've done meters per second, which is meters in second, length over time. This is combining three of our basic units here, though, kilograms, meters, and seconds. Later in the year, we're going to talk about units like joules and watts and moments of inertia, which are different types. And we're going to see those units are comprised of many other units. But as far as we're concerned, when you see something with a force, just think of newtons. Okay, but a newton is really made up of this quantity over here on the right. All right. So there's two types of forces to talk about. One's a contact force, one's called a field force. Based on the name alone, you could probably deduce what contact force means. What do you need for contact? You could read it, but you could also think, what do you need for contact force? Yeah, you need some interaction between two surfaces without using the word contact. Interaction between two surfaces. Like me pushing on this eraser is a contact force. You know, somebody opening the door, you're pulling on the handle, you're in contact with it. What would a field force be? You can see this right here, but what could you think of for other examples? Because obviously you have our definition up there. But what are some other examples? Yeah, like a magnet. That's a really good example. Right? If you brought a magnet near something that like metal shavings or iron shavings, you would see the iron shavings jump to the magnet. They're not in contact with the magnet initially, yet they still feel a pull. So a field force, it's between two objects that are separated by some distance. So the electromagnetic force, or in general the electric force or the magnetic force. Other field forces, gravity is a field force. Think about it. The minute I release this stylus, it's not in contact with anything, yet there's a force pulling me down. So gravity's got to be a field force. It's not in contact with anything. Okay? Now, why might field forces be a little bit more complicated to understand than contact forces? Why is it sometimes more difficult, you think, for students later in the year to understand electricity and magnetism? What's the difficult part about that?
Like you can't control it, like you can't push it, or like you can't really like experiment it.
Yeah, it's not as tangible. Exactly. That's what Catherine's mentioning there. You can't pull it. You can't actually see it. It's very difficult to understand. So throughout the year, what we're going to do is we're going to be able to at least see some of these interactions using certain properties of materials. So for example, one of the things I want to do this year, which I didn't get to do last year, is talk about how a current carrying wire produces a magnetic field. And what we can do is we can have a wire coming through a surface. We'll create a surface like a wooden surface, drill a hole through it, have a wire come up, and what we can do is we can put iron shavings around it, and we'll see rings develop. We'll actually see the iron shavings form rings, and those are the magnetic field lines that occur around a current carrying wire. So it's not obvious all the time, so we have to really try to come up with basic ways to understand it. And then if you really study things that involve field forces, like if you're an electrical engineer, it gets even more complicated because then you're looking at circuitry and it's all theoretical at that point. You don't see electrons literally moving in the wire, yet there are electrons moving through the wire that cause you to get some sort of electrical source or power. Okay, so it's not obvious. So field force can be a little more difficult than a simple contact force. Okay? All right. The thing I want to go into, is how we demonstrate these forces that act on a body. that act on an object. And we call this a free body diagram. What did I say a moment ago about a body that's free versus fixed? What would a free body be?
You're able to move it.
Yeah, something that you can move freely, that you can move easily, that's not being impacted by any forces. So like this water bottle, okay, sitting on the table. Looking at the water bottle alone, it's a free body, it's sitting here. Okay, now, clearly there's a force pulling down. What force is that? Gravity, right? And then there's something pushing back up, or else it would fall through the table. So the table pushes back up. We're going to talk about a term that represents that in a subsequent class. Not to confuse you though now, just let's call it force, okay? Because I started naming the forces in the other class. I think it confused people more. We're not even going into those names yet. We will, don't worry, trust me, we'll go into all that. But just to be simple, there's a force pulling down and a force pushing up. That's what's happening right now to that bottle. So, if you were to draw a free body diagram to represent simply that bottle right there, okay, free body diagrams are traditionally drawn with a box to represent an object. The reason we don't use a point all the time, when you study, dynamics, if you go a little bit further, you'll see just using a point. The reason I use a box is to represent where the force is, and traditionally the force of gravity pulls down from the center. So that's how we would draw that force. Question. I'm not going to label it right now, but again, that's the force of gravity. And then pushing up would be the force from the table, pushing back up, and we actually draw that from the surface of the table, where that would be. And it's always at a right angle, so I'm going to actually draw that little right angle in there now. All right? Stuff that we'll talk about why this is when we get to those. God bless you. Okay, but just to simply show you what a free body diagram looks like, that's a simple example. So you don't draw the interacting surfaces. Like the table, you don't draw that below it. We're physically looking at the forces acting on that object. The key word there is on. What is affecting that object? Not the forces that the object produces or anything like that, or anything about its motion right now, but the forces acting on that object. What if I went like this now? What if I pulled on this bottle at an angle like this? How would I draw that force on this object? I'm pulling on the handle like this, but at an angle. I'm not pulling horizontal, I'm not pulling vertical. How would I just represent that on this diagram? Take a stab at it. What do you think? I gave you some hints. I used specific vocabulary. I'm pulling at an angle. So how might you draw that on here? Try and use that context clue. Yeah, so you'd pull, instead of a right angle, it would be an angle like this. So maybe you're drawing like a horizontal and put theta there to show the angle. And you just put a little arrow coming from the corner because I'm maybe pulling from the corner. Or maybe it's a rope attached to the top middle and you're pulling backward or to the left. So maybe this is what it looks like now. We'll call that theta 2. Okay, maybe this was theta 1. They're different angles. All right, so we can represent forces at an angle by drawing in that angle. Now, if you remember what I mentioned to you, we're looking at theta with respect to the horizontal. So we're going to always label theta between the force and the horizontal dashed line. Okay, I'm going to draw something that you're not going to draw. Okay, don't draw this. We're not going to use this. Maybe we'll call that beta. We're not going to use beta as our angle. We're going to use the angle between the horizontal and the force itself. Okay, so you don't need to draw that one in right now. But if you're given something that's between the force and the vertical, and we want to represent it, let's just look at the horizontal by finding the complement angle. Right? If theta 1 were 30 degrees, what would beta have been a moment ago that I just drew? If theta 1, the red angle, were 30, what would that beta have been? 60. Because together they'd make up a right angle. Again, if I drew beta back in here, oops. If I drew beta back in right here, that would have to be 60. Because 60 and 30 makes 90. Any questions on this? So a free body diagram, again, is a diagram representing all the forces acting on an object that's free in space. Okay? It might be fixed, actually. I shouldn't say it's always free. But the object could be fixed with forces acting on it still, like this podium right here. Take a look at this podium. This little arm here is held together with a bit of a little truss underneath. So if I were to draw that podium, the stand right here, it's feeling a force pushing up from the lever. There's a little truss, a little support underneath here. It's pushing up on it. There's also a hinge at the end of it. That hinge represents its inability to be pulled outward. So technically the hinge is pulling this way on that. And now these books right here are pushing down on it. So that would be the free body diagram of this platform right here. Okay, so you could draw a free body diagram of anything. It can be something stationary, it can be something that can be easily moved. Okay, but a free body diagram simply means isolate that object and draw the forces acting on it. Okay, so let's finish up with this last thing here. Something called a force diagram, which represents all the forces in a given scenario, which is part A, as opposed to a free body diagram like part B. So a car is driving. Imagine this is like one of those test dummy cars where they test collisions for airbag safety. The car drives into the wall. It pushes against the wall, right? So we see the force acting on the wall to the right. What does the wall do? Either the wall breaks or it pushes back and it stops it. Exactly. So that's this right here. This is the wall pushing back on the car. This is the car's weight pushing down. This is the floor pushing back up. Technically speaking, you could, instead of drawing 1 arrow here, you could draw 2 arrows, or 4 if you were looking in 3 dimensions, right? Each tire has a force from the ground pushing back up on the tire. Now, if I were to isolate the car individually, this is the free body diagram right here. Since this force is not balanced, see how these are unbalanced, the top and the bottom? The force acting up from the ground is balanced with gravity acting down. Since there's no balanced force here on the car, what do you expect is going to happen? Either the front end of the car is going to, act like a tin can and crush, or maybe it'll hit the wall and just rebound. But it's causing some force backward, which means it's causing an acceleration. And think back to what we talked about. A force is defined as a cause of acceleration. So if this force is not balanced, it means that the acceleration on this car is acting negatively. Well, that makes sense, because the car is driving this way. For it to slow down or lose velocity, it's got to have acceleration negative. That was like when I gave you the example when I run into the wind. If you're out running for a jog and the wind pushes against you, isn't the acceleration negative there? It's acting against you. The wall is pushing it back, so it's pushing to the left. So it would be a negative acceleration, and that comes from, again, this unbalanced force right here. So we look at force diagrams so we can physically understand what's happening in a given scenario or on a given object. Okay? So again, force diagram, free body diagram. All right? That's the only real difference between those two. Is concerned. Since you have 3-3 due tomorrow in class we're going to go over 4-2. So 4-1 and 4-2 are going to be due next week on, I think I put Tuesday because we have off on Monday for Columbus. Okay, they're going to be due on Tuesday next week, just to give you a heads up.